Welcome everyone to our meeting. So IARPC is the Interagency Arctic Research Policy Committee. It brings together leaders from 18 agencies, departments, and offices to enhance collaboration on research under the U.S. Federal Arctic Research Plan. IARPC Collaborations is the public branch of IARPC. It aims to facilitate interagency communication, coordination, and collaboration to advance Arctic science. The Modelers community of practice aims to enhance understanding of the integrated Arctic system through the use of regional and global Earth system models. And today we have a joint meeting with the Terrestrial Ecosystems team. The Terrestrial Ecosystems team seeks to develop a landscape scale understanding of the drivers and impacts of terrestrial ecosystem change. So thanks again for everyone for for joining us today. Let me see if I can go to my
Richard,
slides
I just want to take a second because there is someone who's joining just via phone who won't be able to introduce themselves in the chat.
Okay.
So that 202 number ending in 901, if you could *6 and unmute yourself and let us know who you are. Okay, at any point, feel free to unmute and let us know.
I'll also just jump in and say, I don't know if the person who's on the phone can hear us, the slides are uploaded on the IARPC website. Sorry, Richard, you can go ahead and get your slides rolling. But you would be able to find them there on the same meeting page where you found the Zoom link.
All right, can everyone see that? So today's topic is Arctic wildfires. So northern wildfires became national news earlier this month when Canadian wildfire smoke began to drift over the East Coast metropolitan areas, including New York and here in Washington, D.C. This animation shows our morning forecast for organic carbon optical depth. This is from the NASA GMAO. We produce daily forecasts, weather forecasts of aerosols. I think, and this is just a ridiculously fast animation, I think what this shows is that there's some continued improvement for the East Coast, but there are some effects of wildfire smoke over the Great Lakes in the upper Midwest. I think that's been a continuing thing over the last couple of weeks or so for those areas. So these forecasts use a MODIS-derived product called QFED, which is called the Quick Fire Emissions Database for representing fire emission source areas. So we can see several areas in Quebec, Ontario, and British Columbia, but also in Central Asia and Eastern Siberia. So if I stop the animation, we can see these three areas here in North America. They're not in the Arctic, obviously, but they're in the subarctic. And these appear to be the areas of that have been producing smoke for the East Coast of the United States. I think Alberta had an early fire season as well, and I think that's been kind of the cause for smoke in the Midwest and other locations as well. So I just grabbed these alerts from the Canadian provinces for British Columbia, Ontario, and Quebec, showing the active fire season in those areas and the smoke. So I think my purpose for showing this is to indicate that northern wildfires have local effects on ecology and terrestrial conditions, but they also have far-ranging effects on air quality and atmospheric radiation. So if we look at, this is a figure from the US Forest Service this morning, which shows significant wildfires for the US, and notably, there haven't been any for Alaska, and that's kind of in contrast, I believe, to previous seasons where we've seen significant wildfires over the interior Alaska. And so that's something of interest. So we're going to transition from these weather forecasts to seasonal forecasting and take a step back to discuss prospects for predicting wildfire conditions. So for reference, I've added this figure. This is the widely used Canadian Forest Fire Weather Index system. So when we talk about fire weather, I believe we're referring to meteorological observations, temperature, relative humidity, wind, rain, which are associated with wildfire conditions, but those are combined then with the surface ecology and surface conditions for fuels to produce a fire weather index. And I think we'll be hearing a little bit more about this fire weather index in the upcoming talks here. So I'm going to stop sharing now. And today for our presentation, we are pleased to have Uma Bhatt and her research team. Uma Bhatt is professor in the College of Natural Science and Mathematics in the Geophysical Institute at the University of Alaska-Fairbanks. And so she's going to give us a presentation on her team's research on fire weather forecasting. Uma?
Thanks, Rich. Let me first do a land acknowledgement. We're all from University of Alaska-Fairbanks, which is located on Troth-Yada on the unceded traditional homelands of the Lower Tanana Dene people. And UAF is grateful for the careful stewardship of these lands. Thank you for giving us the opportunity to share our seasonal forecast research for wildland fire in Alaska. I'll provide a quick overview, and Cecilia will speak to dynamical fire weather forecasts using the Canadian fire weather indices, and Josh will share his work on lightning outlooks. As you most likely know, over the past 2 decades, the occurrences of large fires, those over 1 million acres, has increased in Alaska, as shown by this figure. In spring, the Alaska Fire Management Community develops plans for personnel and equipment allocation, which would really benefit from skillful seasonal forecasts. And this work that we're doing began from conversations with fire management through the boundary organization, the Alaska Fire Science Consortium. And the plot on the left here shows the boreal forest in gray-green in Alaska and part of Canada, and the fire perimeters for different decades to really give you a sense of the variability over time. Next slide, please. This research is being done by a group of people which we've called FIWEPS, Fire Weather Predictability Group. And originally we tried to hire a postdoc to do this work, but due to the many delays during COVID, we could not hire a postdoc in time, and we decided to share the work among a group of early career climate researchers and students. And this has actually worked out really well. We have biweekly meetings, which predictive services meteorologists or fire managers attend. That's Heidi Strader and Eric Stevens. And we also now have participation from the NOAA IMETs. So those are the incident meteorologists. And getting that boots on the ground input has been really critical and these managers attend when they're able to come because they have operational duties. And the engagement of fire management has really been invaluable as they're really active in our meetings, and our work has taken a very different path than it would have otherwise. And it's helped make our work more actionable. And steeping our team in this manner of working together also facilitates other collaborations, like the one we've recently developed to evaluate Pan-Arctic seasonal forecasts with Dr. Payush Jain of the Canadian Forest Service. Next slide, please. And so I'll go over our goals are to develop fire weather and lightning outlooks using dynamical models. I'll just say that there's another piece to this overall project where the Alaska fuels are being prepared, and that's actually another group of our overall project. So we're not dealing so much with the fuels, but we're at the end of our project, we're going to put all the pieces together. We are also documenting dynamical model biases with the hope that models will eventually, this will help improve models. And most of the FIWEPS team is investigating the observed predictability of summer weather, since we don't have a really good understanding of that. And they're working on predicting the last day of snow, summer temperature and precipitation, lightning, and the arrival of the August rains, which shut down the season. And these key items that we're focusing on really came about from conversations with a variety of fire managers and NOAA meteorologists. And we need to potentially add statistical forecasts to increase the skill, as the dynamical models still need to be improved at high latitudes. This is my quick overview, and I'll pass it on to Cecilia and then Josh to talk about their work.
Hi, everyone. Okay, so I'm going to speak a little bit more about evaluating the seasonal forecast. And I think we jumped a slide. If you could go back one, please. All right, thank you. So as Uma mentioned, we've been working really closely with the fire management community in Alaska to kind of answer some questions, or to answer these questions. And one of the key points out of this has been that we found that buildup index is a good metric for fire activity in Alaska. And buildup index, or BUI, is one of those fire weather indices in the Canadian Forest Fire Danger Rating System, shown before. And it gives a measure of how much fuel is available to burn if a fire would start. So here we see the climatological BUI for Eastern Interior Alaska in the solid black line. And you can see that it peaks at the end of June, beginning of July, typically. And that also is the peak of the fire season in Interior Alaska, shown by the biweekly fire counts in the red bars. And this occurs during the duff-driven subseason, during the Alaska fire season. So looking at this, we thought, well, maybe we should start with forecasts that come out in May and see how well they do at those 2 to 3 month leads. But again, talking with the fire managers, we learned that no, they really need that information in March when they have their spring meetings. So we kind of did things a little bit backwards at first. We're starting with this more difficult problem of looking at the forecasts in March. And after presenting these results to them for the past few years, they are now interested in looking at the forecasts from May. So we've also been working on the May forecast now too. It's just been a little bit delayed according to what we would have done first. Next slide, please. So we evaluate the forecast by predictive service area in Alaska, and those regions are shown in the left figure. And then to condense my results down a little bit more, I grouped the PSAs into 3 different subregions. And we're using 3 dynamical forecast models: NOAA's CFS version 2, ECMF's CEAS-5, looking at the years 1994 to 2019. And then we're also using Matteo France's System 8, and their reforecasts just go to 2018. And you can see that each model consists of a different number of ensembles. And then we take the ensemble average BUI from each of the individual models and combine that into a multi-model ensemble average as well. And then we look at BUI forecasts based on those fire subseasons. Next slide, please. And we've evaluated quite a few different skill scores, but this slide just shows the ROC skill score for the different models here. For the ROC skill score, a value greater than 0.5 means that they're skill, and closer to 1, the better. And in these graphics, the March forecasts are in blue, the May forecasts are in orange. The top row are the skill scores for the individual models, and then the bottom row is the skill score for the multi-model ensemble. And again, I've looked at this in a variety of different ways. I've broken them down by subregion, which is the left column, by subseason in the middle, and then by BUI tercile on the right. And that just means above average BUI, or below average BUI. But the 2 key takeaways from this very busy slide are that May forecasts tend to do better than the March forecasts. And for both months of forecasts, the multi-model ensemble is usually greater than any of the individual models.
So Cecilia, just to clarify here, these are forecasts that were initialized in March and initialized in May. And do they characterize then the entire fire season or a particular month in the fire season?
So looking at the different subseasons is the middle column of plots. And then what I kind of look at is I'm looking at where there's skill, for example, in the Eastern Interior regions. So that's so for the subregion and the BUI tercile plots, that does take into account the entire fire season. Okay. So yeah, it's kind of just a way to move the data around and see if anything is standing out. But yeah, so when I'm looking at just looking at the skill in the subregion, that does take into account all of the subseasons. Whereas when I'm looking at the subseason in general, it's like opposite. I'm looking at just the wind subseason, for example, but I'm looking throughout the whole state. I hope that
I see. Okay, that's fine.
Is a clear answer. Okay, thank you. Next slide, please. All right. One of the other parts of my work has been creating operational summer outlooks for the fire managers. So the March 2023 outlook for the multi-model ensemble is this top row. And in these plots, PSAs in green means that BUI is forecast to be below average. PSAs in white are average, and then PSAs in red means that BUI would be forecast to be above average and enhanced fire activity would be expected. The bottom row is the May 2023 outlook, and this is actually the first year I've created the May 2023 outlook. So you can see that in the 2 months time period between these forecasts, something has happened, and the forecasts are showing pretty different conditions for the state. So at the end of the fire season, I'll get observational data, and then I'll compare what was forecast to what happened, and we'll be able to dive into this a little bit more. Next slide, please. The final part of my work is trying to figure out where these dynamical models can be improved. So again, just another snapshot. This is the Duff subseason, so the peak of the subseason, temperature and precipitation anomalies of each of the individual models in our work compared to ERA5. So for temperature, regions in red would mean that the model is warmer than ERA5. Temperatures in blue means that the model is cooler than ERA5. And then for precip, the more green and blue means that models are wetter than ERA5. And so you can see I think the big takeaway here is that at the high latitudes, the models still are missing something compared to observations and compared to the ERA5 data. And then I thought that it was really interesting that CFS and Météo France actually show some similar patterns. For example, they're still predominantly warmer than ERA5. Northern PSAs are drier than ERA5. But with CEAS5, it's kind of a reverse pattern. And so that's something I would like to dig into a little bit more, but I also think it highlights the benefit of these multi-model ensembles so that these model biases are dampened out a little bit. And then the hope is to use some of this information to go back and recalibrate the forecasts and hopes that that improves skill. And with that, I'm gonna pass it over to Josh to talk about lightning.
And the next slide. Thank you. So yeah, hi everyone, thanks Cece. I'll be talking about this connection on our fire triangle between weather and ignition, whereas Cece's been looking at like weather and fuel, right? And so yeah, the main goal of this portion of the research is to develop subseasonal to seasonal outlooks for lightning, and to help inform the fire managers. And so that would be like 2 to 8 weeks. And so, yeah, the main thing here for this slide is to just show you when and where the lightning is happening. Lightning ignitions are responsible for the majority of the burned area in Alaska additionally. So like, that's why we're so interested. We've seen the May forecast for BUI were above average across the state, but then we haven't had, maybe the extreme lightning events that we're looking for. But I don't yet have a lightning model or a prediction yet, a seasonal outlook. So we weren't able to combine that with our analysis. So yeah, that's kind of like to highlight the importance of lightning in our seasonal fire outlooks. And so this figure in the top right shows the concentration of lightning strokes per unit area. So it's just like all the strokes historically in our data set and how many happened. And this is done by the PSAs. And for the rest of the analysis that I'll be presenting on, the results, it's all conducted just for the Eastern Interior PSA subgroup. Future work, we're planning on breaking it out by individual PSAs. And then this plot on the bottom is showing us when the lightning happens during the year, right? And so I marked May 1st on the plot about like day 121. And this is the natural log, the mean natural log of the daily stroke count. So by day of year. And then I've broken this up into like halves of the time series. So the first half goes from 1986 to 2004, and then the second half, 2005 to 2021. And I was just interested to see, hey, are these curves the same? And we do actually see that they're not exactly the same. They, roughly line up, but we do see an increase in the more recent half during the early and mid-season. All right, next slide. Yeah, thank you. So to start this work, I was looking at these self-organizing maps, and the self-organizing map is useful for a couple different reasons for this research. First, it reduces the dimensionality. So basically, I have all this gridded data, but it's really hard because each pixel can kind of change independently in more flexible models, right? You can't run a multilinear regression for every pixel. It'd be way too many. And so the SOM says, hey, what if I broke that down into 2 dimensions? And so it makes this grid. Those are the 2 dimensions of the SOM. And then the other nice thing is that it self-organizes these patterns. And so that we have modes of variability that are similar to each other occur near each other in this 2D space. And in other words, like, it preserves the local topology of the original data set. Similar days should appear near each other in this SOM grid. And so initially, we were just looking at this for the 500 HPA geopotential height, and basic fancy way of looking at pressure. And we're looking at these SOM patterns over Alaska, and they were qualitatively helpful for our work. But they weren't giving us any very much like quantitative predictability. And so what I did was I said, hey, I'm going to run a SOM to reduce the dimensionality of a bunch of different variables like temperature, pressure, right? And I'm going to use those reduced dimensionality. I'm going to use where each day lands in that SOM grid for each variable as a predictor in a random forest classifier. And I'm going to see, can I predict based on where we are in the natural variability of these variables, if we'll have lightning in that day, and if we had lightning, how intense that will be. And so this flow chart just shows you kind of like a broad overview of that model flow. And then, so just kind of call this the SOM RF model. And next slide. And so now here, these are just some of the initial results for the work. The top table here shows the confusion matrix for the intensity model. The second table shows confusion matrix for the binary lightning day or no lightning day model. And then the very bottom table is a summary of some of the performance metrics for these results. So to note, I'm using the F1 score, or the F score rather. I've been using the F1 specifically. The F score is broader. And this is partially because there's some class imbalance, and the F1 score handles that. And then the other thing, important context for this is that for the intensity, because we're looking at high, medium, and low, medium, and high. Sorry, I did that backwards. Lightning days. There's 3 classes for that classifier. And so the F1 score ranges from 0.33 to 1, where 1 is the best score. But then for the binary classifier, it actually ranges from 0.5 being the worst to 1 being the best. So higher the score, the better. And the nice thing about the F1 score is that it balances this weight between the precision and the recall. But additionally, we can tune the F score. So we can think about like an F2 score, which would tune towards the recall. And the recall is the model's ability to identify a lightning day and say, hey, that is a lightning day. And then the downside of weighting towards the recall would be that you're going to end up with more false positives. It's going to take days that weren't lightning days, or weren't like extreme, weren't the high tercile lightning days. And it's going to say, hey, that's a lightning day when it wasn't. So really, this is something that needs to be discussed with the fire managers. And one of the reasons that it's been really helpful to work with the fire managers is because we have to make these sorts of decisions a priori. We have to, we have to control what we're trying to model for. And so that's, an important aspect of the work that we're doing. And then next slide, please. And then lastly, I'd like to share kind of this result that emerged from the collaboration that we've had in the PhiWebs group. So first, this plot on the left, I was looking at just what does the pressure, the 500 HPA geopotential height look like on the most extreme fire days? So I took the top 5% of fire days and took the average of those pressure systems. And we can see that we get this circulation around this low in the Gulf. It goes counterclockwise. And the high above that, we see like a localized easterly flow over Alaska due to this pressure system. And then one of my colleagues in the fire weather prediction group, he was looking at seasonal burned area and the most extreme seasons. And then he took the 500 HPA wind anomalies for those most extreme seasons. And he came up with this plot in the middle. Yeah, that plot from Rick Later. And we see this same result happen again. Counterclockwise circulation over the Gulf with easterly flows over Alaska. And so the similarity between these two results like really popped out. And then lastly, there was actually some work that another one of our collaborators, Peter Bieniuk, worked on, a 2016 paper looking at MODIS hotspot counts and kind of a case study of weather patterns for the highest hotspot days. And the nice thing about this paper is that they made this connection between Rossby wave breaking and this high over low pattern that we see in the other two plots. And so, it was really striking to see this result, and it gives us a lot of direction into where we'll be looking for the seasonal predictability for fire weather, and in terms of both season-ending rains and lightning. Yeah, it's just like it's so connected, and it's been great working together in this large group. And then finally, I'll just pass it back to Uma to close us out.
Thanks, Josh. Thanks, Cece. I think one of the few take-home messages I'd like to leave you with is it really takes time and investment to build human infrastructure and relationships. And we really couldn't have done it without being funded since 2016, first by NOAA and then by NSF to get as far as we have. And we could not have done it without the work of the Alaska Fire Science Consortium, which is at UAF and the International Arctic Research Center. They help matchmake between Alaska fire researchers and management across the US and globally. And we couldn't have done it without the consistent interactions with the fire managers. They've been coming to our meetings since 2016. And to do actionable science, you need to be open-minded about how to solve a problem. You may have to take turns. It may take more time than a standard research path, and I think we need to acknowledge this. And some of this time is needed for fire management and researchers to understand each other and then to decide how to focus the research. And finally, seasonal forecasting is a very challenging problem. And I think it can be really hard for students who would prefer tidy pieces of work for their PhD. So I appreciate my students having patience and persistence in getting through this. But I think it takes place where all the different pieces of the Earth system come together, which I think makes it exciting. And while progress is incremental, I think we need to appreciate that. And it's incremental, but it's really so important for society. Thank you for your attention.
Thank you, Uma, Cecilia, and Joshua for that great presentation. I have a lot of questions. If you have questions, I think the most expedient thing to do usually is to raise your hand so that I can call on you. Or you could simply unmute and get my attention that way. But to start us off, Uma, I was wondering if you could say a little bit about the stakeholders, these fire managers. Could you say how they use your information and what kind of information they're interested in? Some things like that.
So I see some of the fire managers are on here, so they should jump in if I misspeak. I think
Fantastic.
I've been asked this question, like, how do they, we're not at the stage where I think we can quantify how Cece gives the forecasts in March. And I don't think we're at the stage where we can quantify how that is used to make a decision, right? That is the goal of science. And we're asked by our funders, how are they using it? And I think at this point, I don't know. But I think where the stage where we're at is we're in tune about what we need to do to help them make decisions. I feel like that's very solid at this point. I think once our skill gets better, once we have lightning outlooks, I think then it'll be easier to answer that question. So I don't mean to push it off, but I don't have an answer to that.
So
Yeah.
you think that they're kind of in a look and see and kind of evaluation mode at this point?
Well, I think when decisions are made in fire management, and again, I think Kent is on, you can interrupt me if I'm wrong. It's one piece of many pieces of information, right? And I'll say one thing. This year, when the May forecast was being done, we had a FIWEPS meeting, and the two fire managers, Heidi and Eric, were there, and they showed us what was going to be their forecast. And I felt like it was the first time we were weighing in on a forecast, and it made me very nervous as a researcher, because that's not my thing. But I feel like we're slowly progressing, and I think they made based on the El Nino and our understanding of climate variability and CC's May forecast, they made a slightly different forecast than they might have otherwise. So I did feel that we came to a different moment recently.
I'm not seeing a Kent on the participants list, but Kent, if you'd like to unmute and say a few words about how you might use these data.
Kent was here. Maybe
Or not. Maybe he hung up.
Maybe he hung up.
Okay. How long you have a question?
Yeah, thank you very much for the very a nice presentation, nice, interesting work. I was wondering, for comparing to like the forecasting of mid-latitude, like California wildfires. So is there any unique challenge for the forecasting of the Alaska or Arctic wildfires?
Cece, do you want to take that?
Yeah, so I know I've briefly spoken with some people who have tried to do this forecasting in California, and it's my understanding that they are more focused on wind. It's wind events that are driving a lot of the wildland fire in California, you know, especially for the power companies and utility companies to like shut off the electrical grid so that there's, you know, electrical lines aren't snapping and starting those fires. Whereas in Alaska, you know, the majority of acres burned are from lightning ignitions. And part of that is because we have huge amounts of land where people don't live. And so in some cases, fires are allowed to burn and it might not do any damage, but in other cases, they can get out of control or they get too close to urban areas. So there's this big give and take in Alaska too. Not only are we interested in different meteorological conditions, but the fire managers do have to kind of see, like, is this a fire worth suppressing and spending all of this money on, or can we let it burn? And I think in the lower 48, especially, that's not a decision that they usually have to think about. They probably react to the fires much quicker than many of them up here.
May I follow up on that quickly? I mentioned the lightning as the major ignition mechanism. Looks like based on Josh's results, looks like the model predicted lightning is sometimes pretty bad. Is that related to particular process in the model or other things?
So yeah, the prediction that my model is working on is it's how do I put it? It's more intended as like a really broad scale like diagnostic tool. And so we actually haven't evaluated its ability to predict into the future yet. One of the next steps of my work is actually to take the dynamical forecasts that CC has been working with and to plug them into my model essentially and see, hey, do we actually get reasonable counts for the number of lightning days or the number of the highest turf style of lightning day? And that's just something that hasn't been evaluated yet, but we're right up at that step and definitely a question that we're looking to answer.
Great. All right. Thank you very much.
Thanks, Alan. I see a lot of hands up here, but I just wanted to follow up on that quickly. So you showed the lightning count. I would assume then there's a lightning detection network for Alaska that you're comparing against. Can you say a
Yes.
few words about that?
I could say many words.
What is the coverage?
It covers most of the state, but how do I say it? There have been updates to the network, and I have made corrections for some of the updates in that network. And it was a caveat that I try to make with the seasonality plot, which is the average for that day of year, how many lightning strikes we had, and where I broke it up into the 2 time series. Not every single upgrade to that detection network has been made. I guess I should also say it's a ground-based network.
Right.
The major change was they changed it in 2012 to a new system. But yeah, there's a lot of very particular aspects of the network that have to be taken into account when doing the analysis. I will say for the core of the analysis, I'm not actually doing any sort of time series prediction. I'm not saying, it's not saying, well, next year is 2024. What does it look like? That's not an input. And so actually, I'm not too worried about some of the upgrades biasing the results too much. In fact, I'd mostly just be worried that the older system, the data is less robust and we'd actually be missing some information. And so, yeah, it would be nice. I guess, how do I put it? The detection network in Alaska was originally intended as an operational tool. Its purpose wasn't to gather data for research. So we've really repurposed it for that. And it's actually
you've been using you've been looking at the Wildfire product. Have you been trying to do some comparisons between that and the Lightning Network?
I have not yet looked at Modus. That's
Okay.
not part of the lightning work that I've done so far. There's somebody else in my group, or there are several other people in our group who do look at Modus, but we haven't connected those pieces yet.
Okay.
Okay.
Xingyang, you have your hand raised. Can you unmute and ask your question, please?
Yes, thank you for the presentation. It's really good. And I learned a lot since I'm working from the methane emission side. And so I don't know too much about the fires in Alaska, but it seems to me all the fires happen in the interior. And I'm wondering, I think one of the questions is for the forecasting, how long before would the forecast do pre the real fire season? And the other question I think is more about how would the interior fires affect the methane emissions, although the methane hotspots is in the lowlands, in the wetland lowlands, but how would the emissions, the fires would affect the emissions in the interior, and also I don't know how it's connected to the lowlands.
So I can probably partially answer your question. First, we have the fire regime seems to be changing. Last year we had a high fire year, but 1.3 million acres, I believe, burnt in the lower Southwest, which is almost close to the tundra.
Wow.
So there were lots of fires, early season fires in the Southwest. So that was different than typical years. So it's not just the interior that's burning. So that's one. I guess I honestly I couldn't comment intelligently on the methane.
Right, because we also, for Alaska, we our machine learning models estimate high emissions in last year as well as in 2020. So we are thinking about what could be the reasons driving the recent intensification.
Oh, I see. So do you put any, I guess you input temperature, air
Right,
temperature?
yeah, we have
Right.
temperature in the model, but we don't have disturbances like fire, so that's,
Maybe you do indirectly through temperature and precipitation?
right, the temperature we use is from the Merit 2, and it's not from the, the weather stations, so I'm not sure if it's like coupled in the.
I feel like it should still represent what the temperature is
So,
that summer,
okay,
right? I would think, yeah. I mean, Merit 2 has done well in Alaska.
Keeping in mind that Merit 2 has two precipitation products, right? The Prectot core is the gauge observed precipitation that's used to correct the soil moisture. And then there's the other precipitation that is the model derived precipitation.
right. We use the gauge cooperative, and we also use the soil moisture.
Okay.
Yeah.
So let me ask you a question. So methane emissions go up if it's hot and dry, is that correct?
Well,
That's too simple.
yeah, it's hot when it's hot, and the soil inundation will be like soil getting wetter, and that will control the intensity of the methane emissions.
Okay.
Right. But yeah, there are a lot of questions to ask, and I feel very helpful to learn from the disturbances histories and also the seasonal, because I see the increase of the lightning in the early seasons. So, and yeah, how would that link to the actual fire counts and then to the
I wonder, do you have is your model, your methane model is spatial, right?
right.
I wonder if you could use fire perimeters and to see if the high values of methane coincide with those fire perimeters.
Right, that's a good idea. I'm thinking, yeah, that's a good idea. We could try that, like the build-up index, that maybe one of the factors we can
Even the
incorporate.
fire perimeters are the observed perimeters of what actually burned.
Oh, okay.
So anyway, we could follow up by email.
Sure.
I could tell you where that data is.
Okay, thank you so much.
Thanks. Ben Charles, thanks for waiting. You have your hand raised. Can you unmute and ask your question, please?
Yes, thank you, everyone, to CC, Uma, and Joshua for that very insightful presentation on the work that's being conducted in developing models to predict fires based on the seasonality of our world and the climate change impacts that have cumulative impacts regarding the food security practices of Indigenous peoples within Indigenous lands. So my question is, based on the developing tool that's being put together by the three of you and of course others that are probably involved, how can this tool be ensured that Indigenous peoples have direct access to and the ability to interpret and utilize the predictive modeling systems that are being developed to make informed decisions for the protection of food security and traditional practices? Or rather, in a response to Cece's response to a question about what fires to respond to. The ability for fire managers to respond to wildfires is essential for the food security practices of Indigenous peoples within Indigenous lands, in particular where areas are highly remote, such as Utiaga, Katovik, Atasuk, Kotzebue, and other Indigenous communities where wildfires have seen increased or seeing increases within the years. So really, how can we ensure that this tool that's being developed is accessible to Indigenous peoples? And thank you again.
That's a great question. We have a student who's going to join our project this fall, and as the last part of her PhD, she's been working in the YK Delta, and she's interested in linking fires to food security. And she's been meeting with Chalista elders for a few years now, and that the fire and food security has come together in her mind. So we're going to have somebody working on that, but I hadn't thought of it as a tool. I had thought of it more from the research side, but maybe we can follow up on what kind of tool would be useful, because I'm sure Amy would be interested in that. And Amy's maybe on the call.
Thank you for that answer. It's a really great response. I love it. Do appreciate it.
Yes, Amy's that A there.
She's giving the thumbs up. Thanks for your question. Peng Qian, you have your hand raised. Can you unmute and ask your question, please?
Hello, can you hear me? Oh, hello, can you hear me?
Yes, I can. Yeah.
Oh, okay, great. Thank you very much for the great talks, and this is very informational. I'm just curious if you see, since this is seasonal forecasting, seasonal analysis, I'm wondering if you see any signs or trends in seasonal shifts of fire activities in the Alaska. In our research, recently we analyzed the Arctic AOD climatology and trend and extreme event statistics using remote sensing data and also like AOD data and also OMI AI data, which could capture the absorptive aerosol trend over the Arctic. And we see, and also the reanalysis, 3 aerosol reanalysis. So we see a shift of I guess smoke events from early season, like from spring to summertime, basically. So, but our research is based on the MODIS era, basically, which covers 2003 to current, and which is only 20 years. And we kind of speculate that this shift we see in the fire events and transport of smoke into high Arctic is due to like better control on agriculture burning in the early season, especially Siberian area, and also in general associated with climate warming in the Arctic region, which induce more lightning events. So I'm just curious if what we see in our analysis is consistent with your observations or not. So, and how much of agriculture burning in the agriculture burning in fire activities in the Arctic, like how much percentage it sounds for fire comes. Thank you.
Thank you. If I understood you correctly, you said your analysis has shown that the seasonality has shifted a little bit later because of better controls on agricultural burning. Well, there is, as far as I know, there's very little or no agricultural burning in Alaska. So most of it is natural. And while we don't have many cases, we have had the last 2 extreme fire seasons. We had the 2022, we had a very early start and a lot of acres burnt early on, but then it shut off at the end of June. And then in, I guess, 2019, we had a very late fire season that continued and burnt. So I guess if I had to make a generalization, I feel like we see things spreading into the shoulder seasons more than it has in the past. So it might be a very regional view one needs to take to look at the seasonality.
Okay, thanks for your question.
Yeah, thank you for the comment. Yeah, I was also like, if I could follow up, I know that you specialized maybe Alaska region, is this seasonality of lightning mechanism also seen over like Canadian Arctic, and you see consistent behavior between the two regions, or different? As we see the Canadian fires start really early this year.
Right.
Thank you.
Thank you. I think the high latitude Canadian fires are very similar to the Alaskan ones, but Canada's forest is very big. Like it gets into the subarctic a lot also. Well, I guess Alaska's subarctic, but it goes much farther south. So there are differences there, and Quebec's been on fire this year, and that's also a kind of a different ecosystem. So my answer would be, we're similar to certain parts of Canada, but we can't describe all of Canada because Canada is highly variable. And I haven't really looked at lightning in Canada, so I'm not sure. I don't know, Josh, I don't know.
No, I've only been looking at the Alaska Lightning Detection Network data set. I haven't looked at a Canadian one. I haven't looked at satellite data. While the Alaska Lightning Detection Network is capable of it gets some coverage, they don't report the strokes that occur outside of Alaska. Yeah, they only
And we look
report
at the Yukon, which is kind of similar to Alaska. That's
Yeah.
probably the one area we look at. So our view is a little bit limited in order to understand it. Sorry, Richard, you were going to say something.
No, that's fine. Thanks for your question. All right, I had a couple of questions for Cecilia. So you indicated that in your seasonal predictions, you were looking at fuels such as duff and things like that. How do you go from the meteorological variables of the seasonal forecast to quantities associated with the forest fuels?
We're using the Fortran code that magically appeared on my desk one day. So no, yeah, I don't remember who developed this code. Uma, you're muted.
Sorry, let me interrupt here. Maybe there's a misunderstanding because in the Canadian fire indices, it's all meteorological. There's no fuel input. It's really evaluating the readiness of the fuels to burn. So you still need ignition.
So they take the meteorological variables then and infer something about the fuels then based on so they probably need some time period then to understand how things are drying out and things like that. Is that right? I see.
There's those different indices refer to different layers in the atmosphere, and the BUI is really the long time scale. That's the one you want to look at when you look at a seasonal forecast. You can look at I can't remember the acronym. You can look at what's happening in the upper layer in the next few days. So that's a shorter term issue, but it's the BUI that integrates it through the depth of the duff layer.
I see. Okay.
Yeah, they have like these equations that have been developed, and it essentially takes into account like soil evaporation and stuff like that. But we've borrowed it from the Canadians.
So some of the seasonal forecasting systems, of course, keep track of things like soil moisture, things like that. Have you tried to look at those more enhanced variables? I think they might even have the information about vegetation, things like that.
I have not, as part of the forecasting. I'm not entirely sure if others in the FIWEPS group have been using those variables.
I feel like right now we're just trying to get temperature and precip right. We want to get those right first, because soil moisture at high latitudes is a bit problematic. I think the times I've looked at it, I
don't think it's just high latitudes, right? Seasonal forecasting, I think in their reviews, they discuss the fact that they have a lot of difficulty getting precipitation right over extratropical lands in general.
But
So
soil moisture really adds predictability, right, to your seasonal, to the short term, longer term predictions. So getting that soil moisture right is so important. But
absolutely, yes. I think Hazel is going to tell us that we've reached the top of the hour. If anyone needs to go someplace at the top of the hour, we've just reached that. I think we're going to go on here for a few minutes more. What was I going to say? You use kind of an eclectic list of seasonal forecasting systems. You have 2 Europeans and the Weather Service system. So how do you get a hold of the European forecasts then? Do you have some agreement with them, or how do you do that?
I get the data from the Copernicus data system.
Copernicus, okay,
Yeah,
so you get it from there. I see.
And I don't know if it's because I'm like affiliated with the university that I have access to it, or I can't remember, but yeah.
I thought the seasonal forecasts are public. It's the short-term forecasts that are not. That's my understanding. You have to have a special dispensation to get the weather forecast.
That might be true, but of course, there's also the North American Multi-Model Ensemble. Have you thought about looking at that?
That is what we started with.
Oh, and you didn't like it. Okay.
There's a long story there, but that's what we started with. And no, the MMME was great.
Okay.
But one of the things is having all of the variables that we need because of the way the Canadian we weren't able to use all the NMME models because they didn't have all the variables.
They didn't produce the variables.
Yes. At the time resolution that we needed. So that limited it. And then I think part of it was the choice. Well, we used CFS v2, they had everything. And I think as NMME has transitioned to a different location, it's harder to get the data. But
okay.
I will not go into that. And so the Copernicus we were able to get the data for those 2 European forecasts.
I see. Okay. All right. Any other questions? Any comments? I think this is really good.
Yeah, thank you. This was a great
Thank you.
discussion. The attendees were so interactive. It's great.
Great. Thank you so much, Uma, Cecilia, and Joshua. Do we have any announcements, Wilbert?
Not that I'm aware of.
I think we are going to take our summer break, so we won't have a meeting, I believe, for July. But we will be back in August. I think that's our working plan right now. I'd like to thank everyone for attending and participating, and again, thank our speakers. And I think that'll do it. And thank you, Hazel.
Thanks, everyone.
Okay.
Thanks, everyone. Thank you.
Hazel.